Hello everyone, welcome to the channel, and today I have a very interesting problem finally after discussing a lot of properties in number theory about perfect squares and divisibility, and finally we'll see an application of those properties in a real problem. This is a problem where we have been told that if n is a positive integer that has digits 0 and 6 only, so the digits of n can only be either 0 or 6, then we have to prove that n cannot be a perfect square. This is a problem that will utilize multiple concepts we have seen in other videos, and as usual I will try to link those videos, but the focus here will be on this problem. So we are given that n is a positive integer. We have seen positive integers a lot before, and j plus 1 digits is my favorite way of writing n, representing n in the decimal system. My usual stuff is to write it down like this, the digits of n. Why am I writing down the digits of n? Quite clearly, because in the problem I have a constraint, a condition on the digits, that the digits can only be 0 and 6. So I can say that a, j minus 1, all these digits can only have to belong to 0 and 6. Really? Is this really true? There is a slight catch here, that is aj has to be identically equal to 6. Aj cannot really be 0. And maybe I should have mentioned this in the other videos where I use this as a representation. It's just additional information, because when I'm saying j plus 1 digits, the first digit in this representation cannot really be 0. Here it matters because 0 is a possible case for aj. If this becomes 0, then effectively, because since if this n looks something like constructed with zeros and sixes, this kind of a number, if the first digit, and this by the way is a 7-digit number, j plus 1 is 7, but if the first digit aj is, or rather a6 here is 0, then because a0, a1, a2, a3, a4, a5, a6, I don't need that. If a6 is 0, then adding 0 to the left of a number doesn't change the number. So effectively you don't need this 0. You start from a5, then it's not really a 7-digit number, it's actually a 6-digit number. This is important to know. So since I specified that this was an assumption, this was a beginning point of my proof that n has j plus 1 digits. If it has j plus 1 digits, then aj has to be 6, it cannot be 0. All the other digits can be 0 or 6, but if aj is 0, this becomes a j-digit number, so the first one cannot be 0. To prove this, I'm going to use a pretty important property, and that is exhaustion and contradiction. So I'm going to use some assumptions on n, and it's easy to use assumptions when the digits are constrained. Contradiction. Well, there should be some dots here because there are not really 4 digits. There are j plus 1 digits. So to use exhaustion and contradiction, I will have to assume something, exhaust all the possible cases, and contradict something, contradict some property of a perfect square to prove that n cannot be a perfect square with this given condition. So we already know a lot of properties of perfect squares from other videos, and that was the whole background to get here. One of the properties we have seen is that that can be utilized here is if we look at these options, like I'm gonna just focus here 0 and 6, and one thing I know for sure is that a0 can either be 0 or a0 can be 6. It cannot be anything else because that's directly from the problem. And we know from the divisibility of 2 that for these cases 2 will divide n. Or in other words, n is even, identical, always. N is always even. When it has digits of only 0 and 6, n has to be even. So this is a breakthrough here. So because now we already have enough information to say that n is even. N as a number is even. We don't know our perfect squares, but n is even with only these possibilities of digits. Then we are going to get to perfect squares. We have seen a property that for an even number to be a perfect square, we need to have n exactly divisible by 4 in one of the other videos. Because n is even, we need to have 0 mod 4. If n would have been odd, you get 1 mod 4. But since n is even, we should have 0 mod 4. This is pretty interesting because now uh, we can utilize the divisibility properties of 4 to create some cases, and you can exhaust those cases and try to contradict some other properties of perfect squares. So what we can do is, if this has to be true, I need this to be true for a perfect square. So this would mean that the last two digits, that's the divisibility property of 4, the last two digits have to be divisible by 4. Now this can lead to some kind of exhaustion because the last two digits will have only 4 properties. Why? Sorry, 4 cases. Why will it be constrained to only 4 cases? Because you have only 2 allowed digits. So this can either be 0, 6, or this can be 6, 0. The last two digits of n. I don't really care about any other digit because the divisibility of 4 wants me to look at the last two digits only. That's the beauty of number theory. Doesn't matter how large the number is. I'm just going to prove it for here. So I will have to exhaust these cases, and I will have to contradict that n is a perfect square. So I did assume n is a perfect square, and then 4 has to divide it, but I can take these cases and prove that that's not possible. Can we do that? I still don't know, but we're getting somewhere. Can we do that? So case 1 is when the last two digits are this, and I don't really need to write this because we already know this, but 0 and 6. Is 6 divisible by 4? Clearly not. 6 gives a remainder of 2 mod 4. Case 2. Is 60 divisible by 4? Slightly edgy. I think yes. A1 is 6, A0 is 0. Is 60 divisible by 4? Yes, it is. Oops. So I cannot really use that thing here because now it may or may not be a perfect square, I don't know, but at least I don't have a non-zero remainder with 4 to say that it's not a perfect square, but I have something else. In one of the other videos, we have shown that if a perfect square ends with 1 0, it has to end with 2 zeros. So if n, I'll just write down the property here, I'm just referring it without the details. And as usual, I'll link the video. This has to be true, but clearly this is not true because 60 when divided by 100 will give me a remainder of 60. It cannot be divisible by 100. So this was not a perfect square. this is not a perfect square either. I have already contradicted two options that I have exhausted. We are getting there, and I have two more cases to contradict to finally prove this formally, and my problem would be done. So I'm going to look at case 3 here, which says A1 A0 is 66. And once again, I don't really need to keep writing this, but I'm doing this for clarity, just being a bit more descriptive so that there is no confusion. 66, like 64 is a multiple of 4, so 66 leaves a remainder of 2. Clearly this is not a perfect square, it's not even divisible by 4, it's just like the case 1 here. So the ones ending with 6's are directly not possible. 60, yeah, it was a bit more, we needed one more property, but I've already exhausted 3 cases and contradicted them from being a perfect square. I just have to exhaust one more case where the last 2 digits are 0, and I will be completely done with the problem. We have made progress, and it gives us hope that we will find something for this case as well. But I'm going to rub this off because for that case, a case 4, you can say I was saving the best for the last because that one will be longer than all this. It's not very straightforward to see that. And you'll see why. The reason is case 4, when the last 2 digits are 0, then yeah, as usual, if I just to be consistent with whatever I've been doing so far, so if this is 0 0, this both of them are 0, the last 2 digits are 0, this is 0 mod 4, 4 actually divides this because 4 divides 100, and we have seen similar numbers in the video on the divisibility of 4. 4 divides it, and the other problem is for case 2 here, I had said that a perfect square cannot end with a single 0, it has to end with 2 zeros. But here I have 2 zeros. So none of the other cases are helping me contradict this. This is maybe somewhere where I'm stuck. Um, slightly disappointing, but we'll get there. Let's hope we'll get there. To think of this, since none of the other reasoning works, we'll need to think deeper and get deeper into number theory. And this was probably the intention of whoever said the problem first. This needs deeper intuition of number theory. We have to kind of think about this, look at it and think about this. This one is not as simple as the other cases. This needs a little bit of recursion, but before that, just a reminder here that I said sometimes, when you get stuck somewhere, your problem is almost there, but somehow still not there, just that one case. Sometimes it helps to revisit the question. Revisit the question. Just look at it. Think about how we got so far and hope that we can get further. Just think about it. We constrained the digits. We said there are only 2 possible cases for the digits, and we said that the first digit has to be a 6. But in this case, you don't have a 6. There's a spark here. There's no 6 here, but AJ has to be 6. So in this number, there has to be 6. 6 has to be there somewhere because 0, all the digits cannot be 0. At least the first one has to be 6. Because this number here, this number, if everything becomes 0, if the number looks like this, then the number is identically 0, and 0 is not a positive integer. This is the corner case. 0 is not a positive integer. Everything cannot be 0, then the number would just vanish. That gives us an idea. I have only zeros here, but I know that n cannot have all the zeros, even if the last 2 digits are zeros. Then I can choose to write n as another number, n1, multiplied by 100, just because the 100 takes care of the last two zeros. And then I'll try to exhaust and contradict n1. That might be easier because I am taking care of the two zeros in this 100. But as I've discussed in another video, like if n is a perfect square and we factor it as a and b are either, like in this case a is n1 and b is 100, a and b are either perfect squares together or none of them are perfect squares. Interesting, right? So 100 is a perfect square, 100 is 10 squared. So what about n1? If 100 is a perfect square and n is a perfect square, n1 has to be a perfect square. So I can contradict that. I can say that if n is a perfect square that ends with the last two zeros, this case, because all the other cases cannot be a perfect square and we are done with that. But if for the last two digits of n being 0, I can write it in this form, then for n to be a perfect square, n1 has to be a perfect square. Think about it. And fortunately, I have more constraints on this. Like, how would this n1 look like? Because kind of imagine it. I've done this in some other videos. I can factor out, since, like, I haven't written that term, but since 10 squared a2 was also there, I factor that 10 squared. I write something like j minus 2 aj plus 10 raised j minus 3 aj minus 1 plus all dots a2 plus 10 a1 plus a0. But remember, a1 and a0 are 0. So this gives me 0. And 10 squared is just 100. So this is exactly why I have this form. N equals this, because this whole part is basically n1 as I've written here. And this n1 has to be a perfect square for n to be a perfect square. But there's something else we can observe from here, and that's pretty important to keep pondering about the problem and everything that's given here and everything we did so far, is that all the digits of n1 are taken from the digits of n. Pretty interesting. When a1 and a0 vanished and I was left with 100 times n1, all the digits of n1 have to be derived from the digits of n. So can I say that all the digits of n1 also belong to 0 and 6? Now we're talking. Now we're observing something. All the digits of n1 can only be 0 and 6 because all the digits of n1 are derived from the digits of n. Very, very interesting. That means I will have some form of recursion here. Why is that so? Because I was trying to exhaust and contradict, and I landed up with a case where I couldn't contradict perfect squares, even though I exhausted all of those cases. So if I have to keep doing this, I will have to exhaust n1 now, because n is almost exhausted if n1 is exhausted. Like, almost exhausted except for n1, and if n1 is exhausted, n gets exhausted because both can be perfect squares together. So since n1's digits are the same as n, I can now focus on exhausting n1, and that means if I have to exhaust n1, then I need something like this. This part is different. This part is already done and used. Now I'm saying that I need to exhaust n1, and n1 has the similar digits like n, and maybe I can use all of those things I said for n, or can I? Well, if they have the same digits, then n1 is also even. Why is that? Because the last digit of n1, that is a2 now, a2 can only be these. So if 2 has to divide n1, 2 will divide n1 because the last result is n1 is even. So, and I'm trying to contradict that n1 is a perfect square. For n1 to be a perfect square, 4 must divide this. So the last two digits, that means a3 and a2, are what I need to be looking at for n1, not for n. So everything here becomes a3, a2. Because I'm now exhausting cases for n1, not for n. N is done except for just only one case. This will be a3, a2 again. A2, a1. But does this really solve our problem? I don't think so, because you have the exact same four cases as you had for n, and you have the same for n1. So these three cases were done for n. We contradicted them. So we can use the exact reasoning to contradict for n1. Sorry, this is a3, a2. We can use the same to contradict for n1, except for this case again. So I was stuck here for n, and I'm also stuck here for n1, because these cases 1 to 3 for n1 will just follow n, but case 4 for n1 will land me exactly where I had landed for n. Where do we go from here? Does this really help much? Yes, it does. Why is that? Because if this is the case that n1 also ends with two zeros, then n1 can be written as another number. Ooh, here's the recursion coming. You can feel it. Recursion's coming here. I had probably explained recursion and recursive relations in the factorial video. We'll try to link that as well. Recursion's coming. N2 again. And once again, N2 will, I can repeat all of this, everything I did for N, everything I did for N1, and I will end up with this, just this one case. Like maybe instead of A3, A2, this will be A5, A4 for N2, those would be the last two digits, but I will end up exactly there. So now if I plug this in here, can I write it as, because N1 is N2 into 100, 100. Ooh, there's a square term. Again, this is 100 squared. Perfect. Now this has to be the perfect square. Because if this is not a perfect square, then n1 is not a perfect square, and then n is not a perfect square. Recursion is coming in here, but even for n2, you can have a case where the last two digits of n2 are 0. So then I'll get another factor of 100. Then the question is, how long does this go on? This goes on until we exhaust all the digits of n. You can feel that because n1 had the digits of n and n2 had the digits of n1, which were in terms the digits of n. So in one way, n2 also had the digits of n1 and n. Same as n. Still zeros and sixes here. I'll do something interesting here. I'll write this as n3 times 100. This looks like a cube, but it's a factor of 10 squared. You might even choose to write it like 10 squared 10 cubed, and using the exponential properties you can swap it and it becomes a square. So even though it looks like a cube, it is still a perfect square. So this n3 has to be a perfect square now. And I will have to keep on doing this until I have exhausted all the digits of n. Let's say nk is the number where I have exhausted all the digits of n. So think of it this way. Now I will use a real example of n to explain this. So n1 was after deleting two digits, n2 was, this was n1 deleting two digits, this was n2 deleting another two digits, this was n3 deleting another two digits, this is n4. So in this case k would be 4 because 4 is where I'm exhausting all the digits of n, and you get this. But is this really possible? No, because aj has to be 6. The first digit cannot be 0. So this would actually mean this. And the only other case is if this was 6, 6. So depending on j plus 1 being odd or even, if j plus 1 was even and I kept deleting two digits at a time, I would be left with two digits at the end, and those two digits would be the first two digits. If j plus 1 is even, and if this means j is odd, by the way, but if j plus 1 was odd, so there would be only 1 6 to have an odd number of digits, and I kept deleting two digits at a time, so I would be left with only one digit, and that would be aj. I don't need this example anymore because we are convinced now that the final number that is left here, and I did say this in factorials as well, that you need some kind of a base condition. Like recursion is only as good if you know something for the end product, for the end result, you have something known. And what we have known here is that the first digit has to be 6. And I can have two cases when basically the last thing that is left here will be either this or this. This is for even digits and this is for odd digits. Just follows from here. So now again, this can be simplified. This is when j plus 1 is even, by the way, and this is when j plus 1 is odd, by the way. So this can be simplified slightly further because aj is 6. So 6 or 6 times aj equals 6 basic 1. So nk is actually this number, 10 aj plus 10k. Sorry, aj minus 1. First two digits. But in some cases, when j plus 1 digits are odd, I don't have aj1. So aj minus 1 equals 0 takes care of that. So I might even write it like that. I'm getting there. We are getting there. You can almost feel it, right? Either this or this. And once again, since this is 6, it's either 60 plus or just 6. Now remember, for n to be a perfect square, n1 had to be a perfect square, and n2 had to be a perfect square, and n3 had to be a perfect square, all the way up to nk. Nk also had to be a perfect square. For n to be a perfect square, we are still at contradiction phase. We want to contradict this. So for nk to be a perfect square, once again 4 will have to divide nk. Is that really true? When nk is 6, we have this case. So nk congruent to 2, I can simply use it from here. This is 2 mod 4. It's not divisible by 4. It's not a perfect square. There you go. Perfect. So I can just delete that case because nk is not a perfect square. But what about this case? So aj1 again, it can only be either 0 or aj1 is 6. If aj1 is 0, then nk is 60. And if aj1 is 6, then nk is 66. There you go. We already have these cases. So even though we couldn't contradict this case directly, we could recursively write it as and exhaust all the cases as these, and finally came down to these two cases that were already contradicted. So hence case 4 is also contradicted, and our problem is done. It's a very nice problem. It's a great application. So, and just to kind of formally end it, this will leave a remainder of 4. Sorry, remainder of 2 mod 4, so this is not a perfect square. And this, it leaves a remainder of 0 mod 4, but there's a single 0. There you go. So nk is not a perfect square, and nk minus 1 is not a perfect square, and all the way down to n3 is not a perfect square, n2 is not a perfect square, n1 is not a perfect square, and hence n is not a perfect square, even for this case, case 4. Everything is exhausted and everything is contradicted, and we have proven that for any positive integer with this constraint of digits being 0 and 6, n cannot be a perfect square, full and final. I hope this made sense. I hope you guys really enjoyed this problem, and thank you so much for watching. You can leave your feedback or questions in comments, or you can mail me. Thank you so much for watching this, and thanks for always being here. Really appreciate it.